All right, so today's topic is stochastic calculus. And this topic is really an engaging one in quantitative finance because it extends ordinary calculus with real variables to calculus that depends upon stochastic processes, and in particular, Brownian motion processes. And so when we are thinking about how to model the value of a stock or of a derivative, such as a simple option or a more complex option, we can model the dynamics of these assets or derivative contracts as integrals of functions with respect to Brownian motion, where Brownian motion characterizes the underlying dynamics of the asset. And so it's really neat to see how we can develop stochastic calculus and relate it to what's familiar to us with ordinary real calculus, but see how there are extensions of the formulas that accommodate the randomness in the increments with which we're integrating. So let's consider just reviewing first Brownian motion with drift. We discussed this earlier in our discussion of stochastic processes. And a standard Brownian motion model is one where we have our process X depending upon the underlying Brownian motion, standardized Brownian motion B of t, with a drift parameter mu and a volatility parameter sigma, or variance parameter sigma squared. And the key property of Brownian motion includes independent increments and the variation of increments of the process being proportional to the length of the increment. So with standard Brownian motion, where we have a drift parameter of 0 and a sigma volatility of 1, the extension of these properties to have essentially mean 0 and standard deviation equal to sigma times t is to have the mean depend upon time with the drift parameter and the volatility or variance to be proportional to sigma squared times the length of the interval. Now, in terms of understanding Brownian motion, it's going to be useful for us to focus on the conditional distribution of the value at time t plus delta as a function of the value at time x of t. And so when we think of a graph of Brownian motion, which is some path, if we fix at a given value t the value of x of t, or maybe I should write this as s, the value of x at time little t, then if we know the value at time little t, what is the distribution, the conditional distribution into the future? Well, this increment, t plus delta t in red, we can just expand that out to mu t plus delta t plus sigma b of t plus delta t. And then we can group the known terms on the left-hand side of the left-hand terms of the second equation, mu t plus sigma b of t. Then we have a term mu delta t, which is a constant, not random. But then we have the increment of the Brownian motion process from time t to time delta t, t plus delta t. So actually there's a typo here. That should be b of t plus delta t minus b of t. And so we have that our delta x increment is mu delta t plus sigma delta b of t. Now, this increment has mean mu delta t variance sigma squared delta t. And for Brownian motion with drift, this increment is exactly distributed as a normal random variable with that mean and variance. And what's useful to think about is what happens as the increment delta t gets infinitesimal. And so if we look at the infinitesimal increment for delta t, then the expected squared value of the Brownian motion increment is equal to sigma squared delta t plus mu delta t squared. This is actually an exact formula. But what's important for us is that as delta t goes to 0, as it becomes infinitesimal, then this squared increment has expectation that's of order delta t, and it actually equals sigma squared delta t plus little o of delta t. So this little o notation means that as delta t goes to 0, this remainder part goes to 0 as well. And if we consider powers of our increment of delta x, where the power c is greater than 2, then this will also be small o of delta t. So expressions that depend upon second or higher order of delta x will actually be comparable to sigma squared delta t. So with Brownian motion and drift, we have the notation for a stochastic differential equation, which is simply the increment of x is equal to mu delta t, or dt rather, plus sigma dB of t. And with this notation, the solution turns out to be x of t is equal to the value of x at time 0 plus the integral from 0 to t mu dt plus the integral from 0 to t of sigma dbs. And this solution sort of seems obvious when we think about how we understand sort of differential equations or with real functions, but it does extend to this solution when we have Brownian motion. And so, as noted there, this is equal to x naught plus t minus 0 times mu plus sigma times b of t minus b of 0. So our sort of integration of functions of Brownian motion sort of have this nominal solution, which seems very reasonable, and will in fact show that this solution is useful, and it actually extends to more complex equations. Now, the more complex differential equations are one where we consider a drift term, mu, that's not a constant. It may vary over time, and it may also vary depending upon the magnitude of the process. So this kind of an extension is quite general. And we can think about the same extension to the volatility. Rather than being a constant, it might vary with t, and it might vary with xt. And with derivative contracts, we have values of contracts which at any given time depend on time, maybe time to maturity, and the level of the process. And apart from those two sort of features or properties of the derivative at time little t, we have a valuation model that applies according to some function. So it'll be very useful to have these generalized drift and generalized volatility parameters. Yes?
How is the second integral defined? Because obviously the first one's the Riemann integral. What about the second one? Is there an actual formal definition of, I guess it's an Ito integral?
Right, and we will get there in a moment. But if we're integrating from, well, here it's from 0 to t. If we're integrating the process over increments, we're basically going to be summing over the increments, although summing on the infinitesimal time scale over the entire period between 0 and t. And so if we break that sum of infinitesimal increments, we basically get the last value minus the first. And so we'll see that come into play. So what we will determine with this general setup, though, is that when we have extended drift and volatility, we then will have a solution to this Brownian motion with drift, with sort of generalized drift and volatility, satisfying this equation. So we're going to want to be able to compute these integrals in a consistent way, and the Ito calculus provides us with that. So we have to define Ito integrals. Well, in defining Ito integrals, we have this notation that we need to be comfortable with. We are going to, first of all, consider a probability process that is defined by this triple. Now, let's see, have any people here taken sort of advanced probability or measure theory? Well, we basically have here sort of a sample space, and here we have what's called a sigma field of sets which are subset of omega. And then here we have a probability model where if we have a subset of omega and it's an element of this sigma field, we have this probability of that set is well defined. So this notation sort of encompasses the generality of probability models that are important to specify and be comfortable with. Well, with the omega set here, these are a collection of little omegas which are possible sample paths of this Brownian motion. And we can think of, okay, here's one path, one possible path. Another possible path actually matches the first path up to time t, but then continues on somewhere else. Another path could be one that is sort of reflected about a given level. We went through this a bit in our discussion of Brownian motion processes. And so we can think of just the collection of all possible paths. Now, the filtration, Ft, we think of script Ft. This is going to be the sigma field of events or paths, which are fixed or known at times s less than or equal to t. So with script Ft, the information up to time t, if sort of this is our path up to time t, the event of following this path up to time t sort of is deterministic if we look back, deterministic for s less than t, but then it's random for s greater than t. So we have a value, or in script Ft, it basically says, okay, we can work with paths that are deterministic before time t, but then are random after time t. And so that relates to the concept of being measurable. So we say that events in Ft are measurable with respect to Bs, with the information set up to time t. So if we consider times before t, the path is actually just a constant, or as a function, a path valued function that's constant. Now, if we have this probability measure on omega, the space of all possible paths, if we consider the sort of conditional distribution given x at time t, then we're trying to specify the model for all future paths that start at the level x at time t. And sort of that probability measure over the entire space of paths can also be restricted to the paths up to time little t. So we can basically focus on probability measures that are unconditional but restricted to the information set up to time t. Now, we'll want to refer to the value of the Brownian motion at time t, and it's important to know that often this notation bt is implicitly the value of a specific path. So to emphasize that, we'll indicate that it's the Brownian motion path indexed by little omega. And so we then want to consider the Ito integrals with respect to Brownian motion. First, where we consider simple functions, real functions, where f of bs is the value of little f evaluated at the position value of the Brownian motion. And we'll want to consider integrating that function from 0 to t. And so this is our notation. So with a sort of companion graph with the same x-axis as our Brownian motion. We could have f being some function which varies, and we want to basically integrate this function f evaluated at the Brownian motion. So actually, this is actually a wrong graph. I thought we had the same graph. We basically want for sort of, let's say, x equals bs of omega, some function. All right. Well, if we consider this notation to represent our Ito integral, we're going to develop the formulas for these Ito integrals. And importantly, this Ito integral is going to have basically a sort of deterministic, simple, real integration term for each path. But the paths indexed by omega are random, and so this Ito integral is actually going to be a random variable. And as a random variable, if it exists, it'll have an expectation and a variance. So let's consider a number of special cases that will define Ito integrals. Okay, the first case is the simple one where f of x is equal to 1. So let me just erase this and have the level 1. So we consider f of x equaling 1. So if we integrate the increments of Brownian motion over from 0 to capital T, let's propose that that's equal to the increment from 0 to T for each path. So the right-hand side corresponds to the sort of simple integral of this path bs of omega between bt between time 0 and capital T. And I guess it's not in the notes, but if we were to consider the integral of 0 to T dbs of omega, we could think of this as the sum from 0 to n of I t over n. Let's see. Let me do this. I equals 1 to n, I minus 1 t over n, the integral from I minus 1 t over n to I times t over n dbs. So here I'm thinking of basically dividing this increment from 0 to t into different increments of width, capital T over n. And if we approximate, or each of these integrals here are basically looking at the integral of, or the change in bs from these lower limits to the upper limits. And so the integral of dbs of omega, in a consistent way or well-defined way, is defined by this increment of the whole process. Now, if that's true, then when we consider the randomness in omega, the expectation of this integral is 0, where b is the standard Brownian motion. And this variance is equal to the length of the interval times the sigma of standard Brownian motion. Well, if we change our function f to be not the constant 1 over the whole real line, but just the indicator of an interval, it's just 1 between a and b. So we have a and b here, and we have basically 0 up to a, and then it equals 1 up to b, and then it's 0 beyond. Then this Ito integral is essentially looking at the change in Brownian motion from time a to time b. So no surprise that that's a reasonable definition. Now, from these reasonable definitions, we can consider a second case where our function f is again a function only of time s, but it's given by a step function over time with steps or levels given by the ai's that are constant. So we go from this single step function here to considering basically different step functions for our function f. Now, these step functions could correspond to like the number of shares held of an asset. And so, this integral could correspond to the gain or loss if the underlying asset sort of followed Brownian motion. But here, with this particular step function, we can define the Ito integral to just be the sum over the increments of the step levels times the increment of the process. And so, that's a pretty sensible definition of the integral, and it would apply if we had assets traveling, values going by a Brownian motion process, and say shares given by the A constants that were maybe deterministic. Now, at this point, we're using functions f, which are deterministic functions of time. We can then extend this to sort of random functions. And actually, before I do so, just notice in red the mean 0 and the variance of this Ito integral of the step function. The variance is simply the sum of the squares of the levels times the length of the increment over which that level applies. So now, case 3, things get more interesting. We can allow our levels AI to be random variables. And these variables, random variables AI, so AI equal to AI of omega. This is a path, and so we can have the levels vary depending upon what the path value is. And so we want the AI to depend on and I guess by depend, I'll say be deterministic on script f t sub I. So if we define our levels to be functions that are in this, are measurable in this information set, then that's what we're doing here. Now earlier we talked about non-anticipatory variables. And so this is a non-anticipatory variable. It basically says that the level from ti on, for whatever that increment is going to be a function of what's happened in the past. So this is like a realizable function f, where when we apply the f function to the Brownian motion increments, we're applying known increments at all times. And so with this case, we actually want to make an assumption of measurability on that ith information set, and we want a bounded squared expectation of the level. So if we have those two properties, then we can write out the Ito integral as this formula, and it will have expectation equal to 0 and variance equal to the sum of the expected squared AIs times TI plus 1 minus TI. Okay, so I guess rather importantly, with these developments so far, we're thinking of the time s ranging from 0 up to time capital T. And we have increments ti plus 1, where this increment is something. For simplicity, we could define this increment to have length, say, t over n for n increments, and have equal increments. But this, this formula for the Ito integral is considering integrating the Brownian motion over the interval from 0 to t. So integral from 0 to t, f of s, bs, dbs. And this is our integral, our Ito process, I of f. And we can write I of f evaluated at a particular path given by this formula. All right. Well, an interesting example, just from a mathematician's standpoint, is what if we define our levels to be equal to the value of the Brownian motion itself? So we're integrating b db. So we're thinking of this example, so case 3, special case 3, integral from 0 to t of b sub s dbs. Well, if we consider sort of discretizing this Ito integral, with these random levels AI, actually I'm getting ahead of myself. This integral will be a limit of these. For any fixed set of increments that we apply this random level given by the value of the Brownian motion on those increments, then for each of these cases with n increments, we get that we have mean 0 and the variance is equal to the sum of the variances of each of the terms. And that turns out to be equal to the sum over the increments of the time increment t level ti times the increment to the next time value. And this sum of ti times ti plus 1 minus ti is essentially equal or close to the integral from 0 to capital T of s ds, which should be a half t squared. Yeah.
How do you conclude that the expectation is 0?
Okay, the expectation is 0 because each of these increments here have expectation 0. So we're assuming b of 0 is 0.
Yeah, but what if, AI is not independent? Because like when you take the expectation inside the sum, you get.
Okay. Okay, yep. Let's see. Okay, AI omega is an element of f sub ti. So it's constant on f sub ti. So let's see. So AI of omega and b ti plus 1. This increment into the future from time ti is independent of the past. And so its expectation, if we take the product of these two and take expectations, we can take the expectation sort of given, or the expectation over ti times the expectation sort of given, let's see, over ti plus 1 given ti. So we can break down this expectation into its decomposition, and the expectation of this factor conditionally will be 0.
Yeah, that makes sense.
So, yep. All right. This case 4 is the case that essentially defines Ito integrals in general, which is if we consider taking the limit of integrals with respect to sort of step functions with random levels ai, but then allow the increments, the time steps, to get closer and closer to each other, then the limiting value of this Ito integral of the step functions is equal to the Ito integral of f. So we have in our special case where f of x equals x, f of the Brownian motion is the Brownian motion itself, we end up getting this formula. And here we have basically the sort of discretized value of the integral. And then what's of interest is to see how the limit of that equals this formula. And so to prove this, there's a nice mathematical trick. And so if we look at this term on the right-hand side here, which is an element of the sum, it turns out to be equal to a half the difference in the squared values at the endpoints of the interval minus a half times the difference between ti and ti plus 1 squared. So this is simple to verify. It's trivial, but incredibly useful. And so if we sum over all the time points from 0 to n minus 1, we get the sum of the first terms minus the sum of the second terms. And so this first term is actually a telescoping sum. When you sum the terms, there's cancellation of the middle value in successive terms. And so we're left at the end with the 1/2 the square of the last term here minus the square of the very first term with I equals 0 here, which is 0. So this is a half bt squared minus b0 squared, which is 0. That's the first term. And then for the other, we have minus a half the sum of the squared increments. And so if we know sort of what the last time interval term is, Tn, that's capital T. And then we have the same terms on the right. And what's important to know is that the limit of the sums of these increments converges to T, capital T. And this was the property of the total variation of Brownian motion over any increment. If we look at the sum of squared values of increments and take the limit as the number of increments grows large and the sort of partition gets finer and finer, then the limiting value of these sums of increments is equal to capital T. So this is our formula now for the Ito integral of b dbs. And let's see. So what's really important to highlight is that this is not equivalent to thinking of the Brownian motion process like a real function where we're integrating b db or x dx, which is x squared over 2. We actually have this drag on the integral that depends on the variation of the process. Okay, now we want to generalize to the general case of Ito integrals. And so what we do is we consider defining the Ito integrals from 0 to t f of omega s dbs. But then we want to basically consider this to be a process xt of omega. And we want to generalize this to an xt of omega where we're integrating just up to time little t. So what we want to do is, once we have this definition for the Ito integral over a fixed interval from 0 to t, we want to be able to define the Ito integral where we're integrating only up to time little t less than capital T. And so in order for this kind of function to be well defined, it will turn out that we need some very strong mathematical arguments. And there's a book by Steele, chapter 6 on sort of quantitative finance, where he does go into all the details. And I have to admit, it's not really a fun read. It's sort of interesting to look and see what's involved so you know how important it is to sort of be a good mathematician if you want to prove things. But fortunate for us, they're proven well and we can apply them. So what do we need? We need that the function little f needs to be measurable. Script fs, the information set up to time s measurable for every time s. And we want the integral of the squared f over time, where that's for each fixed omega, we can integrate the square of f and then take the expectation of that. We want that to be finite. So this term here, this expectation, is taking the expectation over the probability model given by capital P. And for each omega, we're integrating the squared f over time from 0 to t. And we want that to be finite. So with this notation, we basically are extending our Ito integral over 0 to capital T with the Ito integral from 0 to little t. And we can define this by just replacing our f function in the Ito integral I of f by simply the function f times this indicator from 0 to t. So that step basically chops off the integration at time little t and gives us our definition. Now, let's see. Okay, the definition of this extension of our Ito integral over 0 to t to integrating it over 0 to little t's for any little t less than t, that's relatively straightforward and intuitively obvious. What's not necessarily obvious, though, is that our process xt is a martingale with respect to this stochastic process model given by the Brownian motions. So if we look at what it means for a process to be a martingale, if we look at the conditional expectation of the time t plus k value given time t, then it equals the value of the process at time t, little t, plus the integral of the process from time t to t plus k. And we're taking expectations, conditional expectations of that given xt. And so the expectation of this future sort of increment from t to t plus k is basically integrating a function times increments of the Brownian motion, where our function values depend on the past and the increments are independent in the future with mean 0. So this expectation turns out to be satisfied. And if we look at the conditional variance of the t plus k value given xt, then it's equal to the expected square of this f ds. And so when you look at the variance of the discretized sum of increments, you get the discretized sum of variances of those increments, which are f squared, and then the dbs squareds are dt. So this simplifies for the variance to that term. And okay, all of this is fairly, I know it's like mathematical results, and it's sort of like, who cares? Well, it turns out that this variance turns out to be a squared norm of our function little f on the space of the probability space of paths across the time increments. And so okay, actually I'm going to get ahead of myself, but let me get ahead of myself and basically comment that this norm of our function f is going to be a squared norm on the space of Ito process integrands. And let's see, those of you who have taken, I guess, real analysis or metric spaces, you know, what's an important value of norms? What do we do with norms or squared norms? Well, with norms, we can talk about limits of elements of the space and talk about whether limits exist. And so with this setup, we actually will have the space of Ito processes, and we can calculate the squared norm between different Ito integrals. And so we can characterize limits in those spaces and be guaranteed that those limits exist. So with this sort of motivation of defining useful norms on different spaces, we have this Ito isometry, which is, if we look at the variance of Ito integrals defined by integrand little f, then those squared norms, or the variances basically of the Ito processes, is equal to the L2 norm of the integrand little f. And if we write out the definitions of these sort of squared norms, we get these equations. And what's relevant here is being able to express our variance of the Ito integral as the squared norm of the integrand f. So we have limits and convergences of sequences of Ito integrals, and something that's important mathematically is if we take the limits of these Ito integrals over increments that are getting a grid of increments that's getting finer and finer, do we have a unique limit or not? And so that's what's important, and is the squared norms and convergence properties are used to prove that. So we basically can talk about closed linear subspaces with these norms on the space. So what this does is it allows us to define sort of the distance between different integrands, f, and the existence of a limiting Ito integral as we consider increments getting infinitesimal. All right. Well, we can think of this Ito integral as a Riemann sum, a limiting Riemann sum. And if we have time steps ti, for simplicity equal to it over n, we can consider the limiting sum of f of the Brownian motion times the increment of the Brownian motion. And this sum actually converges in probability as n goes to infinity to the integral. So, so we have a limiting value that exists, converges in probability. And if we consider, I guess, the covariances of the x process given by these Ito integrals from 0 to little t, then these will, or this xt will be a mean zero Gaussian process with independent increments. And the covariance between the process at time s and time t will simply be equal to the integral of the squared f over the times where they both are non-zero. So, all right, so we take a partition from 0 to t, we get this result, and we can prove that the limit equals the this integral notation. So basically, there's a limit that exists, and this is a notation for that limit. And Steele goes into a lot of the details for that. Now, what's of interest is that we can now consider sort of some general Ito cases, which will be referred to as Ito's formula for different kinds of functions f. And so if we consider first the case where f, little f, is a real function mapping reals to reals, then if it has a continuous second derivative, then we can express the function f of bt in terms of its sort of Taylor approximation, and we get this formula, which is Ito's formula for f of bt. And in looking at this expression, what's relevant is that, okay, the first term f0 is a constant. The second term is a Gaussian sort of process integral. It's an integral of Brownian motion. And then the third term is the integral of the second derivative of f, evaluated at the BS value. And so we have an adaptive sort of drift term. And we can prove this formula, or outline the proof by saying, okay, let's consider the Taylor approximation of f at x plus delta x and expand it to second order terms plus a remainder. And then if we take the difference of f at time t with b minus f at time 0 with b, then we're looking at the sum of the increments from time t1 to tn, and those increments are equal to the sums of the derivative of f times the increment of time plus a half the second derivative of f times the squared increment plus the remainder terms. And if we take the limits of those, we get the integral of f prime dbs plus a half the integral of the second derivative. So Taylor series gives us this formula. And we can think of developing a notation with Ito calculus, which is that our sort of differential of f at bs is equal to f prime of bs dbs plus a half f double prime times at bs times the squared of db, which is equal to ds, the increment of time. So this is our Ito's formula shorthand. And this shorthand corresponds in a similar way to derivatives and antiderivatives, where sort of here's the stochastic differential equation, and here's the solution to that stochastic differential equation on the top. Now, what's really neat and very powerful is that if we want to solve for the integral of a function, so suppose our objective is to solve for the integral from 0 to t f of bs dbs. Well, if we have the antiderivative of little f, so that means that the first derivative of capital F is equal to such that f prime is equal to f, then if we choose the antiderivative with f of 0 equal to 0, then we get f of bt minus f of b0 is equal to this integral of the derivative of f dbs plus a half the integral of the second derivative of capital F, which is simply f prime. So this formula is what we just derived for Ito's formula. And if we solve for this first term on the right, then that's equal to f of bt minus a half the integral of the first derivative of f prime of bs ds. So what's neat as a sort of technique in stochastic calculus is that if we want to integrate a function, little f, of bs dbs, then we can just apply Ito's formula in reverse and characterize it as the antiderivative of little f at bt minus a half that, defining the antiderivative to have f of 0 equal to 0. Now let's apply this just for the case where capital F of x equals x, capital F prime, the derivative is 1, and the second derivative is 0. Then the integral of dbs is equal to bt. And let's see. So basically, the integral of bs dbs is equal to capital F of bt, which is bt. and then plus minus a half the second derivative, or the first derivative, the second derivative of f, which is 0. So this gives us this result. And if we consider capital F equaling a half x squared, then little f is equal to x, and little f prime is equal to 1. And so we get the integral of bs dbs is f of bt minus that, which is a half bt squared minus a half t. So this gives us sort of a verification of the limiting results we went through before with these Ito integrals. Okay, the next step is to extend Ito's formula to functions of more than one variable. So we basically want to go from sort of f of x, so one variable f's, we want to go to two variables functions f, and we'll write the notation of s comma x, which maps basically, let's see, the time space cross the time range r plus cross the real line of x into the reals. And we're going to consider functions little f that are continuous to different orders in terms of the time variable and the space variable. So we have this notation C super 1 comma 2, meaning that it's continuous with first order derivative existing and continuous, and second order derivative with respect to x and continuous. And so we have a Taylor series for increments of this function little f now of two variables, which has the multi-dimensional d equals 2 Taylor series formulation. And it equals the f without the increments on t and x plus delta t times the partial of f with respect to t plus delta x times the partial of f with respect to x. And then we have the second order partial differential terms, and the only ones that are going to be of interest are the second order partial of f with respect to x, which will be multiplied by delta x squared. The other second order terms will actually be of small order delta t. And with this second order Taylor approximation, we're able to derive that the function f of t bt is equal to the initial value plus an integral over time of a function of the Brownian motion ds plus an integral over increments of the Brownian motion plus 1/2 this integral of the second partial of f with respect to dx squared. And this integral here ends up being multiplied or being integrated with respect to the increments of time, because the delta x squared terms are infinitesimally equivalent to increments ds. So, so for this formula, we have here, if we look at the difference in the little f function from time 0 to t, it equals the right-hand side. So this top formula here is simply taking this second order Taylor series and looking at the increment from 0 to t and what that equals. And what we get is a sum of two terms, an integral with respect to time of the partial with respect to time plus the half, the second derivative of f with respect to x. And with this notation for the value of little f, what's important to notice is that if the argument in the time integral, if that's equal to 0, then this will be a martingale, because the second term is an integral of terms times increments of the Brownian motion. And the increments of the Brownian motion all have expectation equal to 0. So we'll have the possibility of this function being a martingale if that's true. And this integrand equaling 0 is equivalent to this partial differential equation on the little f. So there's this connection between martingales and partial differential equations for f when we're thinking of a process f of t. So if little f is a martingale, it will turn out that the partial of f with respect to t will equal minus a half d squared f dx squared, which is a PDE condition. Now, the other thing we want, actually, for this to exist is that the variance of the function f of t bt, which is bounded by the squared expectation, is finite. And so this will be finite, the variance, if that second term has finite variance. And so for that to have finite variance, the variance is the integral of the square of that argument df dx with respect to time. And so, all right. Now, what's interesting with this Ito formula is we can apply it to a function, little f, which is the exponential of sigma x minus sigma squared t over 2. And importantly, well, let's see. This partial of f with respect to t does equal minus a half sigma squared f. And so this is actually a partial differential equation for little f. But df dx is equal to sigma f. The second partial of f with respect to x is sigma squared f. And Ito's formula, if we expand it out, gives us this expression for little f. And this function, little f, is in fact a martingale. If we look at the expected value of f given f of 0, 0, it equals 1. Now, f of 0, 0 is the exponential of basically 0, which is 1. But this function f, little f, if we plug in bt for x, it's a scaled log normal random variable. So this little f evaluated at x equal to bt, so it's a transformation of the Brownian motion process paths bt by this function, is actually a scaled log normal random variable. And so e to the sigma bt minus half sigma squared t is a scaled log normal. And the expected value of this e to the sigma bt is actually equal to e to the 1/2 sigma squared t. We proved that, I believe, in a problem set. And so the expectation of f of t bt is going to actually equal 1 for all t. So this little f is in fact a martingale. Now, let's see, with Brownian motion with drift, the ruin problem, we can actually use some sort of Ito process ideas to deal with this problem, where we assume that xt is a Brownian motion with drift, mu, and variance parameter sigma squared. So here's its formula, stochastic differential equation for xt. And we're interested in what's the probability of stopping at A before B, where the stopping time tau is the first time t that hits A or minus B. And this argument is one that's very typical of quantitative finance developments, I guess, by mathematicians. It's actually a very neat argument where I don't think I could ever have derived this, but the derivation using martingale theory is really very elegant. And so let's consider trying to solve for this probability by using martingale theory. So let's consider a martingale. Let's try to define a martingale with value h of xt, defining mt, where the tau is the same stopping time, and the condition on h is going to be that if we sort of are at the value xt equals a, then the probability is 1. And if we start at minus b, the probability is 0. So this is fixing the sort of terminal conditions of the function h when it hits the limits a or minus b. Well, we can, if we have a martingale that satisfies this function h of xt, then the expectation of the stopped martingale is simply equal to the probability that x tau equals a. And by the martingale property, the value of, or the expectation of the stopped time is equal to the m0, the initial value of the h function. Now, the initial value is the value when x is equal to 0. So we're starting at 0 with the x process, and it either moves and hits a or hits minus b. So in order for this h function to be a martingale, we have to have that the PDE condition is satisfied on h. So the partial of h with respect to t is equal to minus a half the second partial of h with respect to dx. And so if this h function, which is the probability of hitting a first, depends just on the value of xt, then it equals h of mu t plus sigma bt, substituting in for what xt is. So we can work with the function little f equal to h of mu t plus sigma x. And if the partial of f with respect to t, which is by chain rule mu h prime of mu t plus sigma x, if that equals the second partial of f with respect to x, the second partial derivative of h with respect to x is sigma squared h double prime, then this PDE condition says we have this relationship, this differential equation for h, although it's in the first derivative of h. But we can then rewrite this as the second derivative of h evaluated at argument y is minus a constant times the first derivative of h. And so we can solve that equation by noting that sort of h double prime over h prime is equal to d by dx of log of h prime. So the derivative of the log of h prime is a constant. The solution to that is a linear function. And so we then end up being able to solve for little h of y equaling this formula. So this is the solution to this problem. All right, let's see, we're at the end of our lecture today. So next time we'll finish up these notes talking about standard processes where our sort of a function for the drift and our b function for the volatilities have to satisfy certain properties. And if you read ahead in these notes, you'll see that we need the probability of sort of integrating the drift over time has to be finite and absolute integral. And the integral of the squared b's have to also be finite. If those were not finite, then you would actually have sort of explosive behavior of these integrals, which where they won't exist. So these are reasonable properties to assume for those. And anyway, we'll go through some interesting results here with this particular problem, and then turn on to stochastic differential equations next time. All right. Thank you.